Alright, so we're going to talk about inference for slope. I'm just going to go through these notes and then feel free, if whoever's controlling the video, if it seems like you or other people in the class say, hey, can we pause the video, that would give everybody a chance to see the screen and take some notes, or you can talk as a class about what I said, if something was confusing, and then just resume when you're ready. So I am going to go maybe a little faster just because I'm not really going to stop, just because I want to make the video as short as really reasonable. So yeah, feel free to pause. So it says, our final hypothesis test will be for the purpose of identifying if there is enough evidence to show there is some kind of rate of change, or slope, between two variables. Therefore, most of our time, our null hypothesis will be that the slope is 0, or that there isn't any rate of change between two variables. Then the alternative hypothesis will be that the slope is not 0, or that there is some rate of change between two variables. And another thing that I'll say here, and I'll kind of write this in here actually. Another thing that we'll use for rate of change or slope is when we write our null and alternative hypothesis, we're going to use the word association. Because if things are associated, they have a slope between them. But if they are not associated, then like the scatter plot's just going to be more or less random. Doesn't look like there's a slope between the two variables or a rate of change. So they're not associated. Okay, so our conditions for slope are very different. So you have to make sure you memorize these. So conditions for slope are nearly linear, so the scatter plot must look pretty much like a line. Independence, that one data value, because it's a certain number x and a certain number y, that really doesn't have any bearing or relationship with a different value that has a different x or a different y, or the same. Equal variance, no pattern or shape appears in the residuals plot, so we'll look at a plot of the residuals and make sure that there's not some type of pattern that appears. So everything is more or less like scattered throughout. It's not in a shape. Nearly normal, the histogram of residuals is nearly normal. So we just want to make sure that when we make a histogram that it's unimodal and symmetric, that it's not significantly skew right or significantly skew left. And actually, there's a couple examples in your textbook that go through some where the histogram of residuals is a little skew right or skew left, but then in the comments it said it is skew right, but not skewed right enough that we would be concerned. And so they just make that comment. So if you get something that is unimodal and not symmetric, like it's a little skew right or skew left, it's not a huge deal. It's if it's bimodal, like they're like clustered around the outside, or it's significantly skew right, then it's an issue. Okay, so remember this printout where we have just a computer printout of some measurements from a linear regression analysis. So this is taken from the number of semesters of education beyond high school and salary in thousands of dollars for 24 randomly selected individuals. So just right off the bat, I'm just going to label what that says a little bit. So you have number of semesters, that's going to be your x variable, and that's going to be what we are predicting salary. So we're predicting our y variable for salary. And then our n is 24, and I just want to make this comment now. Our degrees of freedom is going to be n minus 2, because this is a t-test. So degrees of freedom would be 24 minus 2, so 22. Okay, and then a couple other things here. So just to remind you of some things, we've got your constant is pretty typical to see, and then your x variable is the other one. So this would be like if you were writing an equation in your algebra days, y equals mx plus b. Your b, or your intercept, is that constant, and then your slope, your m, is that other one for semesters. But on your formula sheet, it doesn't use m and b, it uses b1 and b0. So just to put it in terms of those, your b0 is your intercept, so this is b0, and this is b1. Okay, then some extraneous information. We're not going to use this, we're not going to use this, and we're not going to use this. And we won't use the r squared adjusted. But everything else we will use, even though the t and the p is not essential. That's kind of nice to know. Well, actually, the t is essential, but the p-value we're going to get or use the calculator to show. But the rest of the stuff I wanted to label before we move on to the rest of these questions, because this S, I don't know if anybody remembers this, but capital S, this is the standard deviation of residuals, which we actually need to check, because if you remember, one of those conditions was we have to check the distribution. In this case, if this was all the information presented to us, we wouldn't be able to check that histogram. But just to point out, that's where the standard deviation is. And then r squared, we'll talk about that in a second. So, equation for the least squares regression line. This is a semester 1 question, but it is very likely to show up on your next test. And it will show up very likely if this was an AP Stats question on linear regression for inference. They're probably going to want you to write the equation first. So this equation is going to be y equals, and then m, or b1, is 1.1594. Might as well just write all the decimals. You could round it to 9, that's fine. Times x plus the intercept with a constant, so plus 34.018. All right, and that's it. And if they said write it in the context, or actually we probably should write context here, so we could either write y and x. I think I have a laser pointer somewhere on here. Yeah, so I could write this value, or sorry, the x and the y in terms of, like, is it semesters or is it salary? So y is going to be salary, predicted salary, and this is going to be number of semesters. Actually reminded me, it is predicted salary, so we need to put a little hat on the y so we know this is a predicted value, not the actual y. Okay, so let me just go over to the side and write x is equal to number of semesters and then y hat is predicted. It's important you have that predicted salary. And it's kind of a pain to write on the iPad, so I'm not going to write it, but you could write in thousands of dollars too. So sorry if it's going to be kind of hard to read. So help each other out. See if you can guess what I wrote. Maybe sometimes for some of these, especially when we have to write, that's going to be a pain in the butt. I don't know if I want to type using the... Yeah, we'll get there. So interpret the slope. So if we're interpreting the slope, we need to do something with this number. So I like to write it like you did in Algebra 1 days. So 1.1594, it's always rise over run, so it's that number over 1. So we want to interpret that, like I said, rise over run. So this is like the y, the rise, over the x, the run. So what does that mean? That means for every increase in one x variable, there is a predicted, it's important that you have that word predicted in there, increase, sorry, this is terrible writing, of $1.1594 thousand in salary. Yeah. Okay. Yeah, you think this is bad handwriting, but I've seen some of your handwriting, and it's pretty atrocious. So, okay, so so this is your y variable, $1,000 in salary. And then, so this is like the y. I'm writing it this way because this is basically like a copy and pasteable outline. So your y variable in this case was y, or sorry, I did this wrong. For every increase in x, there we go. There is that in y. In x was number of semesters. Increase in one semester. So for every increase in one semester, there's a predicted increase of $1.1594,000 in salary. Perfect. Okay. Again, feel free to pause as I go through this. So identify and interpret the coefficient of determination. So that is r squared, and up above it said that r squared is equal to 0.33 or 33.5%, but I'm going to write it as a decimal, so 0.335. And interpret it just means write as a sentence. So this is a semester one thing, but I'm going to try and write this. 33.5% of the variability of the y variable, so the y variable is salary, is accounted for by, and then you could say the linear model, the least squares regression line, the equation. So I'm just going to say by the linear model. Okay. Correlation coefficient, that is r, not r squared. So r is the square root of 0.335, which is 0.579. Okay, then standard deviation of residuals, that's capital S, which is 7.37702. You just leave it at that. That's all we're going to do with that. Just want you to know what it is. Okay, so let's go to page 2. And of course, this is going to do that to me, so I need to delete all these somehow. I think if I do this, well, that's going to delete all of it. Sorry, I need to get rid of stuff. Okay. Let's see what that does. Can I erase that? Okay. I'm sorry, that was terrible. Okay. Now, page 2. This would be a typical AP Stats question. It's going to give you most of the information instead of giving you everything in like L1 and L2 and having you do the regression yourself. It's going to give you all the information you need. So this says a consumer organization has reported test data for 50 car models. We'll examine the association between the weight of the car and the fuel efficiency. Here are the scatter plot, summary statistics, and the regression analysis. Is there strong enough evidence of an association between the car weight and the gas mileage? So let's start with the state step. So state, we need to state the null and alternative hypothesis. So null hypothesis, we're going to assume there is no association between, I'm going to abbreviate it, between car weight and fuel efficiency. Okay. And yeah, I know it says the word association. Think of that. That's what we say when we write these formally, but think of that as slope. There is no slope or there is a slope. It certainly looks like there's a slope if you look at the scatter plot. Like it looks like things are trending in a certain direction. It's not like all randomly everywhere. So the alternative hypothesis, there is an association between car weight efficiency. Okay. And they didn't give a significance level, so we'll just go with 0.05. And I'm actually not going to do the, sorry, I gotta get rid of this, I guess, because it's not, I'm not going to do the, sorry, sleep deprived. What am I not going to do? Oh, I'm not going to go into detail with the plan of each condition, but I'm just going to list them. And I'll have you do the same for, like, when you have to deal with the, like, the test and everything. You don't need to list all the conditions or anything. Sorry, I'm trying to figure out how to lock this. I should have done this before I made the video, but I really don't feel like starting over again. So how can I do that? Lock. That sounds like the right choice. Let's see what that does. Now if I move it, does it move? Still moves. Okay, well, you know what? I'm just going to delete it. Okay, you've got it on your page. Now, plan. Okay, so this is a line regression t-test. The conditions are nearly linear, independence, equal variance. I'll just list them out first and then I'll make some comments on them. Like I said, we don't need to write it out. I just want to tell you how would you check them if you wanted to write out, like, the details on all of them. Okay, so nearly linear, that means you're looking, oh, that is so annoying. Okay, whatever, you deal with it. So nearly linear means that you're looking at the scatter plot and things should look like a line, and they do. They're trending down. It's not like all over the place and look like a parabola. Second condition, independence, just that, like, this car has this certain weight and this fuel economy. Just because it has that weight and fuel economy doesn't mean that it's going to affect this car's weight and its fuel economy. They're two separate cars. So even if they're, like, from the same brand, even if they're, like, both Chevys, doesn't matter. They're two different cars, so they're independent. Equal variance, you'd be looking at this plot. So it's actually kind of nice now. I think I might like that it's here. Oh, look, I can move it. Okay, sorry. ADD. Okay, so we've got equal variance. Just looking at this. Are things trending a certain way, or is it pretty much all over the place? We want it to be all over the place. We don't want there to be a pattern with how things differ over time. So we want, and that's how it probably would fail if it ever failed, is you'd have things really close to the line here. And then as you move to the right, things would be more scattered over here. And then finally, nearly normal. The histogram of the residuals is nearly normal. So you're good to go. Okay, so I think I'll just delete this again. So, and now write the do and conclude. So the do part of this, it's a t-test. So you need a t-distribution. Kind of looks like a normal distribution. We just label it with degrees of freedom. And that's 48. It says it right here. 48 degrees of freedom. And so we are assuming that there isn't a slope. We're assuming that the slope value, I'm just going to put B1 because that's what we use for our slope. Our slope value is 0, but it turns out the slope was negative 8.21. So that's somewhere over here, negative 8.21. And so then we're shading in this side. It's kind of off center there. There we go. And then normalizing this to a t-distribution. The t-distribution still has 0 in the center, but the t-distribution is over here on your computer printout, negative 12.22. They normalized it for us. So that's a point in between there. Yeah, you get the idea. So, but whenever we do one of these tests, we assumed there wasn't a slope, but we're trying to show there is a slope. So just because it turned out that from this test we got a negative slope, we still want to account for what's the possibility that we could have gotten a positive slope. So this becomes a two-sided test, and all of them will be a two-sided test. Unless you say something, we assume that there is a negative association or a positive association, then it'd be one-sided. Let's see. Okay, so we got that. Now we need to write TCDF. So TCDF from negative infinity to negative 12.2. Those are negative. Degrees of freedom 48. It's two-sided, so it should be 2 times. And then your, oh look, now it's staying. So your p-value, it says it over here, it says less than or equal to 0.0001. That means it's incredibly small. So, and actually if you plug this into your calculator, I did that earlier, you get something like ridiculously small that the calculator doesn't even tell you a scientific number. It just says 0. It's too small for the calculator to even show it. So when that happens, that could happen for the future examples too. Just don't say it's equal to anything. Just say it's less than 0.0001. That's fine. So just saying it's really small. So now we're ready to conclude that we have our p-value. So let's use blank. That's fine. Conclude. So with all conditions met and a p-value of less than 0.0001, we reject the null hypothesis, meaning, so now you interpret the alternative, meaning we have enough evidence to suggest there is an association or slope. That's how you should think about it. That's how we write it formally, as an association, but think about it. There is a slope between, we want to provide context, between car weight and fuel efficiency. Okay, perfect. So now, finally, a typical AP Stats question, I was thinking about it, like they might have you do some of these details. They'll probably have you write the equation of the line. But they would also probably say something like construct a confidence interval for the slope and explain why that confidence interval, the way it turns out to be what it is, why that confirms your conclusion. So in order to create the confidence interval, just to remember how a confidence interval is even made, from your formula sheet, it's always a statistic plus or minus a critical value times a standard deviation of a statistic. So tailoring that to a regression slope problem, this is going to be your statistic is the slope. Plus or minus a critical value is going to be inverse t, since it's a t distribution. Inverse t of degrees of freedom, comma, area, comma, degrees of freedom, times your standard deviation of slope. Okay, so let's figure out what that is for this problem. Your slope, as mentioned before, and it's in your computer printout, negative 8.2, what was it? Negative 214, plus or minus. We're going to do inverse t of 0.995 with degrees of freedom 48. And so you plug that into your calculator and you get 2.682. Standard deviation of the slope, that's up here in the printout. That is this value right here. Here's slope, weight, and then coefficient. That's our slope. Here's the standard deviation of the slope, so 0.6738. So we'll write that in there. 0.6738. And so you plug that into your calculator and you get this interval. Negative 10.021 and negative 6.407. And that's a, how can I erase that quickly? Good. That is a confidence interval, 99%. So if it said interpret the confidence interval, we could say we're 99% confident the true slope for cars' weight versus fuel efficiency is somewhere between negative 10.021 and negative 6.407 miles per gallon, or whatever that is. Or not even miles per gallon, it would be weight per fuel efficiency, so that's kind of weird. But it's negative, and that makes sense. So as cars get heavier, fuel efficiency decreases. So, but we're not asked to interpret it. What we are asked to do is say why those numbers, why that confidence interval confirms our hypothesis test, our conclusion, which our conclusion was there is an association, there is a slope existing here. So what we're going to say, over here to the side, we are going to say that since the slope value of 0 is not contained in the interval, it makes sense that we had enough evidence to conclude, I butchered that one bad, to conclude an association exists. So, like if an association didn't exist, then a slope value of 0 should exist in the interval. But since the slope value of 0 is not in the interval, and to be honest, not even close to the interval, it makes sense that we had enough evidence to conclude that some type of an association does exist. So I think I've got on my iPad here, this is 28 minutes and some change, so it'll probably be 29 by the time I'm done. But I think I'll stop there for today. So Monday you'll just do this far, and then Tuesday we'll do the last page. Actually, whoever's filling out the class reflection, if you could tell me how the video worked. I know when my wife was doing some videos for her class, it was like the feedback from touching the pen to the iPad was kind of loud. So just tell me if that was like too distracting, that it was just really pointless to do the video, or if it was bearable, just annoying, or I don't know, just give me some feedback there. And just tell me how things worked and anything else that's I should know. Other than that, good luck. We'll pick this up tomorrow.